The next thing we're looking at, maxima or minima problems, a field of mathematics which I guess is more practical. It's more what we call applied maths. So it's also known as optimisation methods. I've done another course at uni which was called optimal control theory, things like that. And basically it's about finding the most efficient solution to problems. Now, the way we do it, we use our calculus, but the advantage now is that we don't actually need to draw the graph of the function to find where that maximum turning point is. We can use the calculus to find it. So what do we need to do for the sort of problems we're going to look at? So we'll have a problem, and we're probably going to reduce it down to a set of equations, usually a bare couple. Now, one of those equations will be what it is we're trying to maximise or minimise, the best solution that we're trying to find. And so it'll be obvious in the question. I'll say, what's the greatest area, or something like that. The other one, there'll be some actual information given to us that we can link the variables together with. Now, once we've got that, we'll then try and rewrite this equation that we have, that we're trying to maximise and minimise, as a function in terms of one variable, because then we can go and use our calculus to find the maximum or the minimum. Okay, so here's a typical sort of problem that you have out in society. I'm sure you've had this problem yourself. You know, you're sort of on the weekend and you've got this piece of rope that's 36 metres long, and you decide, you know what? I want to cut this rope into two pieces. But I'm not just going to cut it anywhere, because when I get the two pieces, the first piece I'm going to make a square out of, and the second piece I'm going to make a rectangle out of it. But just to make it interesting, that one of the sides of the rectangle will be the same length as the square. Now, I want to do this in such a way that I maximise the area, because maybe I'm going to capture ants or something and put them inside our little pens where ropes is the fences. As I say, a very typical sort of problem. I often like to draw diagrams to visualise my problem. So there's my two bits of rope that have been formed into a square and a rectangle. And I'm going to creatively give it some dimensions. S for the side of square. How I came up with that, I'll never know, but you know. Now, we know that the rectangle also has a side of S. I'll call the other side R for rectangle. Yeah, clever, hey? So, all right, let's come up with some equations. My first one, well, they're trying to maximise, or we're trying to maximise, the areas. So the area of the square would, of course, be S squared. The area of the rectangle would be RS. 36 metres is the piece of information. So my rope, which would be 6S plus 2R, if I was to unfold my two bits of rope there, that's what I'd have. We know that's got to add up to 36. So, all right, I need to eliminate either the R or the S out of the area equation. I want it in terms of one variable. And I want to make life easy for myself. It's going to be a lot easier to eliminate the R than it is the S. So the second one, I'll make R the subject. And we get R is 18 minus 3S. Substitute that back in. There's my equation, tidy it up. We actually end up with a quadratic. Now, of course, that does mean we don't need calculus, which kind of makes it a silly example when you think about it. Because we could use our quadratic theory on that one. If we were to draw that, we'd have an upside down parabola. We just want to know where the vertex is. Let's pretend we don't know that. Okay, so we're going to use calculus to do it. So, right, there's my function. I'll find dA ds, the first derivative, to locate my stationary points. I'll find d2a ds2 to go and classify the stationary points. We know the stationary points are going to occur when dA ds equals 0. That's when s is 9 on 2. Well, the second derivative is a constant -4. Kind of makes sense, because if we've got a parabola, it's going to have a constant concavity. That's less than 0. So I know that when the side length of the square is 4.5 metres, the area is a maximum. Notice I didn't bother working out the area. The question didn't ask for it. It simply said, what's the length of the square? But I tell you what, that in itself is interesting, because if the length of the side of the square is 4.5 metres, What's the length of the side of the rectangle?
They're both squares.
It also turns out to be 4.5. And there's that optimization that often happens, that the optimal solution is often the perfect shape. All right, let's do a different one. We have an open cylindrical bucket. It's important that it's open because we want it to hold the largest possible volume of liquid. Of course, if it was closed, it wouldn't hold any liquid at all. It'd just go everywhere. So, okay, we're going to make a bucket. We're lucky because we happen to know that the amount of material we have to make this bucket is 12 pi units squared. We've measured it. It turned out to be an irrational number. It turned out to be 12 pi when we measured it. The other amazing thing is we can use every single piece of material. There's no wastage at all. We're going to use every piece of material to make the bucket. Now, obviously, we're looking at a very simplified problem. As I say, I've studied some of this at uni, optimal control theory. In reality, you have to take into account wastage and things like that. So you have more variables and what have you. But this is just a starting point, I guess, of optimization problems. So we're assuming we can use every single piece of material we have available to us. Well, there's my bucket. Radius R, height H. Now, volume is what we're trying to maximize. So pi r squared H. Surface area of a cylinder is, of course, because remember we don't have a top on it. So our surface area would just be pi r squared plus 2 pi rh. We know that's to be 12 pi. Oh, isn't it lucky that we happen to have 12 pi? Pi will cancel. That was lucky. Now, we either want to make R or H the subject of the formula. H would probably be the easier one to work with here. So we'll make H the subject. Everything divides by pi. H is 12 minus R squared on 2R. So volume, substitute in, tidy up. I've now got a cubic. So in this case, I can't use the quadratic theory to find the maximum or minimum. It's a cubic. Okay? Well, there's V. Dividing R, we'll need that. And our second derivative, d2v dr2 minus 3 pi r. We know stationary points will occur when the VDR is equal to 0. I get two possibilities, r equals plus or minus 2. Now, this is where we use a little bit of common sense. This is a practical problem that we're solving here. So I'm not going to test r equals negative 2 because I'm not going to make a bucket with a radius of negative 2. That doesn't happen in the real world. So, logical one to check. Let's just make sure. So when the radius is 2, my second derivative is minus 6 pi. That is negative. So yeah, that will create the maximum volume. Now, what did they actually ask us for in the question? They wanted the volume, they wanted the radius, and the height as well. So we've got r equals 2, substituting into everything. The height would also be 2. Funny bucket. Radius, height, very weird bucket. The volume would end up being 8 pi. So there we go. Maximum volume, 8 pi units cubed, and that'll be when the radius and the height are both 2 units squared. So it's sort of like a short, fat bucket, isn't it, rather than the ones we traditionally see. That's the idea behind these optimization problems. We've got to, okay, get a couple of equations out, then use our techniques of calculus to go and solve the problem.